This video is about the demonstration and designing of bandpass filter for the group 13 of FPGA project. Our project aims to design and simulate and show the bandpass filter on FPGA board and in Verilog as well. To design a bandpass filter, we have used MATLAB as our tool. So to design the filter in MATLAB, firstly we'll open MATLAB. In the command window, we type filter designer. After typing this, there will be a window that will pop up. In that, we can change our response type. For our project, it will be bandpass, and for design method, it will be FIR filter with window FIR filter. Our filter order we have kept as minimum order for any specification that we'll give, and the frequency response, the sampling frequency will be around 30,000 hertz. F stop 1 will be 3,500 hertz. F pass 1 will be 5,000 hertz. F pass 2 will be 12,000 hertz, and F stop 2 will be 14,000 hertz respectively. After that, we'll click on design filter to see the response that we'll get. As we can see, that somehow closely resembles a bandpass filter with a high order in around in 70s. Then next step is that we'll go to arithmetic operation. We'll change the filter arithmetic to fixed point. We'll change the numerator word length to 40. And for filter precision to specified at fixed point settings, the second one. Okay. After that, we'll go to targets. We'll apply it first. After that, we'll go to targets, and we'll generate the HDL code from this window. After clicking on it, we'll get several settings for that, like what is the language that we wanted to give on Verilog, and we can even select the name, change the name of the filter. For example, we are keeping it FPGA project, and then the test bench. We can select test bench. In the test bench, we can select what of type of stimulus we want to give to our filter. In this, we have chosen all the default custom custom responses that comes with MATLAB for our filter input. And after that, we have selected for our filter. After the inputs of our filter, we'll generate the code. This will not only generate the filter, but it will generate the test bench as well for the filter. After that, we'll let it generate first. Yes. Now our filter is generated. Now we'll open Verilog. Yes. So after putting the code into the Verilog, as we can see, we have gotten the code from the MATLAB. In the code, as our order was very high, for example, this filter that we are using, the order of it was 77. And as we can scroll down and see the number of parameters, the number of coefficients, there are 77 coefficients. As we can see in the line 137, there are 77 coefficients. How does this filter basically works is, as we go down, we can see there are multiple add and multiple product wires, which kind of works as they are named as. So these are the delayed pipeline as well. So basically what happens is, as we can see in any one of the code, the product is basically delay multiplied by coefficient. Then this coefficient, whatever we got the product, will add it to the sum. If we go down a little bit, we can see that sum one is around stop. We'll see that sum is add plus this add is just basically product and summation sign extension of product. So after that, basically what it does is it multiplies the signal with the coefficients, and then if the signal rise in the frequency region of bandpass, it will just multiply it with the gain. If it does not lie with that, it just reduces it. So this is how coefficients are working in this case. As we really go down, all these coefficients are being multiplied and then being added. At the end of our filter, we can see that output is basically the sum. In the line 11, yep. In this line, we can see that output is generally basically the sum only, filter output of the filter. Yes. assign output type convert, as we can see sum 68, and it's being just concatenated, the sum is being concatenated, and after that the filter output is just output type convert. After that we'll go to the test bench of the filter. In this test bench, basically we have been given an input as well as what should be the expected output of the filter. If both of them matches, then it works. It means that the filter works. Basically, if our filter output matches with the filter output reference, then it means that our filter is working correctly. So this test bench is basically feeding the data to feeding the input to the filter and just giving us the reference output as what our output should be compared to. So now we'll run the simulation. Yes. And we'll convert all the waveforms into an analog form to understand the signal properly. We'll go to the waveform style and then convert it to analog. If we zoom it in, like it will fit into the window, we can see there are some waves in the filter out. We can see there are some waves. First, let's see in the filter in. As we remember from the MATLAB, the first input that we were supposed to give was an impulse response. The filter in, the first type of input that we are seeing is an impulse type of response. The filter out is the expected response. It's not the expected. It's the output response of the filter. As we go down, we can see various type of inputs as well. If we go down, we can see there's a ramp function as well, and the expected filter response, if it matches with our output, it means that our filter is correctly working. This is how we have generated the this is how we have generated the band pass filter using MATLAB, and as far as we know, our filter works perfectly fine. And uh, and this is the end of the demonstration for the simulation of our filter.